Day 10, we're going to talk about linear programming and building with Legos. So, essentially, this lesson shows us why we would graph a system of inequalities and what it means to have the feasible region as we've been doing that. So, here is the example that we're going to use. We can use Legos to model production in a furniture factory. The company produces only tables and chairs. A table consists of two large and two small Lego pieces, and a chair consists of one large and two small pieces. When determining the optimal production plan, you, the manufacturer, must take into account that there's limited supplies. There are only 6 large and 8 small pieces available. So this is where, if we were in the classroom, I would hand out sets of Legos, and each set would have your 6 large and your 8 small. And I would say, all right, play around with it. How many different combinations of tables and chairs can you come up with this set of Legos? And again, here just shows how these were built. I suppose I can make this big here. So it shows how these are built. That table's the 2 large on top, the 2 small on bottom. The chair is 1 large and then 2 small. Here's kind of what it looks like if you want to picture that. The profit from each table is $16. The profit from each chair is $10. The production manager wants to find the rate of production of tables and chairs per day that earns the most profit. Production rate refers to the number of tables and chairs that this company can produce per day. All right, so there's some important information we're going to underline here. Profit, $16 a table, $10 a chair. Again, we only have 6 large and 8 small pieces available per day. And so we call those, oh, they're right here as well. These are the constraints. Constraints are kind of like what holds you back from making as many as you can. All right, so they're the limited supplies or the constraints. So then it says circle all the combinations that can be made. Use the chart on the next page to calculate the revenue of 4 combinations that work. All right, so again, here's what you're thinking about as you're looking at these pictures. Since we can't build them, we can look at these pictures and decide, yes, this is a possible combination. So you have 6 large and 8 small pieces available. All right, so this one, do we use 8 small pieces? 1, 2, 3, 4, 5, 6, 7, 8. Yes. Do we use 6 large? We have 4. We didn't use all the big pieces. We only used 4 large pieces. But yes, we can make 4 chairs. So maybe I'll circle it if we can use it. All right, so this is a combination that we can produce. We have some leftover supplies, but that's fine. All right, can we build this one? Again, we're looking for 6 large pieces. 1, 2, 3, 4, 5. Okay, that one works. And we're looking for 8 small pieces. 1, 2, 3, 4, 5, 6, 7, 8. All right, so this one works. Again, we didn't use 1, 2, 3, 4, 5. We didn't use all of the big pieces, but we had enough supplies to build this set of 3 chairs and 1 table. Okay. Let's try this one. Again, there are 6 big pieces. 1, 2, 3, 4, 5, 6. That works. 8 small. 1, 2, 3, 4, 5, 6, 7, 8. All right, this one works. Let's try this one. 1, 2, 3, 4, 5, 6, 7. Okay, this one doesn't work because we only have 6 big pieces. So we can't do that one. Can we do this one? 1, 2, 3, 4, 5. Yes, that's less than the 6. Our small piece is less than 8. 1, 2, 3, 4, 5, 6. Yep, we can make 1 chair and 2 tables. Can we build this last one? 1, 2, 3, 4. Yep. 1, 2, 3, 4, 5, 6. Yep. So these ones don't use all the supplies, but we can build them. Okay, so here I've circled different combinations that work. So we can make 4 chairs, 3 chairs, 1 table, 2 chairs, 2 tables, 2 chairs, 1 table, and 1 chair, 2 tables. All right, so it says using the Legos in your, okay. Okay, so you can't do that because you don't have your bag, but we have at least 4 combinations of tables and chairs that work. Let's calculate the profit for each. So now I have to go back up to like the profit equation, and the profit is this: $16 a table, $10 a chair. So I'm going to write that down somewhere here. So the profit is $16 per table and $10 per chair. Let's define our variables. X is the number of tables. Y is the number of chairs. Okay, let's calculate profit. Let's do 4 tables and 4 chairs. Okay, so this is the profit of 4 a good spot to put it? Okay, so I'm just going to put it right here. 4 tables, 4 chairs. All right, so let's calculate it. It's going to be 16 times 4 plus, and it's $10 per chair. So $10 for every chair. And there's 4 chairs here. All right, what is the total on that? So I know that we got 40, I don't know what 16 times 4 is. 16 times 4 is 64 plus 40. Oh, I'm sorry, this is just 4 chairs. 4 chairs and 0 tables, is that right? 4 chairs. Okay, so I did this wrong, this should be 0. So let's make this a 0. Okay, so now let's calculate, that's just $40. Okay, so if we just make 4 chairs, that is $40. All right, let's do the next combination. 3 chairs, 1 table, and I did tables first. Okay, so 1, 3 is the coordinate that I'm looking at. Keep changing colors here. Okay, so let's check. 1 table, 3 chairs. So we're going to plug into that same profit equation. It's $16 for every table plus $10 for every chair. All right, so let's calculate that. So that's 16 plus 30, which is $46. Okay, well, our profit went up a little bit. It went up by $6 if we make 1 table and 3 chairs. All right, let's check the next one, which is 2 tables and 2 chairs. Okay, so 2 tables, 2 chairs. Let's plug in. All right, so 16 times 2 plus 10 times 2 All right, let's calculate that. So that's 32 plus 20, which gives us $52. All right, it's going up. All right, let's try the next combination. So we did 4 chairs, 3 tables. Okay, so that one didn't work. 1 chair and 2 tables. 1 chair and 2. Okay, I put tables first. Okay, so 2 tables, 1 chair. All right, so let's type in. So it's $16 for 2 tables plus $10 for 1 chair. And then as you can see, it starts dropping down again. So this is 32 plus this is $42. All right, and then our last example, 2 chairs, 1 table, we could test, but it's probably going to be lower because we're not using all of our supplies. All right, so right now it says what combination would produce the most revenue, and it would be this combination of 2 tables and 2 chairs for a revenue of $52. Doesn't look great. Okay. So then right here it says the process that we use with the Legos is not very efficient. If we have 900 large blocks and 1,350 small blocks, we would not want to find every combination by building it. It would just take forever. Now we're going to look for a faster way to find the maximum revenue using our amazing math skills. So first of all, how many variables do you think we need? What will the variables represent? And we already defined them, at least I did. Cancel. They are tables and chairs. I called X the number of tables and Y the number of chairs. So I'll just rewrite that. X, the number of tables. Y is the number of chairs. To algebraically represent the constraints of the problems, do you think we should use equations or inequalities? And how come? And again, the definition of constraints, they're limitations caused by scarce resources, time, equipment, amount of Legos, and so on. And they are expressed algebraically by inequalities. So the constraints, we're going to use inequalities because we don't have to use all the pieces. Okay, we can use all of them, but we don't have to. So we're going to use inequalities to set up a table. And it helps to make this chart. When you make a chart, it helps to put your variables on top. So we have tables, which is X, chairs, which is Y. The constraints are on the side. We have 2 constraints, the large pieces and the small pieces. All right, so let's write our constraints here. So with the table, how many large pieces do we use per table? So if we go back and look at our table here, we use 2 large pieces per table. So we're going to use 2 large pieces for every table. How many large pieces do we use for a chair? And if we look at the chair, we use 1 large piece for the chair. So plus 1y or y. And this is our first constraint, the number of large Legos. And we knew that there are only 6 large Legos. I better double check. Yep, there are only 6 large Legos. So that is a constraint that's holding us back from building just like a ton of tables and chairs. So what we use here to make our tables and chairs has to be less than or equal to 6 because we can use all 6, but we don't have to. So less than or equal to 6. All right, our other resource was the small pieces. And how many small pieces did it take to make a table? It took 2 small pieces to make a table. So 2 small pieces for every table. How many small pieces for a chair? Again, it was 2. 2 small pieces per chair. And our constraint was holding us back as we can use up to, but not more than, 8 pieces to make our chairs. Actually, 8 pieces to make tables and chairs. So the small pieces, not more than 8 pieces. All right, so those are 2 of our constraints. So we have, I'll write these down. One of them is 2x plus y has to be less than or equal to 6. So that is the constraint for the large pieces. The other one is 2x plus 2y has to be less than or equal to 8. And there are 2 more constraints. We call them the common sense constraints, so I'm going to write them down, but they're kind of already accounted for in our graph. We cannot use less than 0. So for example, the number of tables has to be greater than or equal to 0. Whoopsies. I wrote that wrong. So x has to be greater than or equal to 0 because we can't have negative tables. And then the number of chairs has to be greater than or equal to 0. So these are called the common sense constraints. In a graph, they're already kind of taken care of when you don't have any negative numbers on your axes. All right, so now it says graph. Graph your system of inequalities on the next page. You can use the cover-up method or solve for y, and you could solve for y and use the slope and y-intercept. Don't forget to shade. All right, I'm going to use the cover-up method just because I find that a little bit faster, but we will review the solving for y as well later on in this unit. All right, so here's my first constraint, the large pieces. To use the cover-up method, I'm just going to cover up 1, make an equation, and solve. Let's redo this so it's a little bit neater here. 2x equals 6, divide by 2. All right, so I am going to graph x equals 3 if I cover up the y. Now let's cover up the other one. Whoopsies. So then we have y, let's set that equal to 6. Oh, and then that's already done. Okay, so using the cover-up method, we can get 2 points and we can graph it. So let's graph it. Notice there's an equal sign there, so it's going to be solid line. So I'm going to find where x is 3 and where y is 6. And let's go ahead and connect those. So at home, if you have like a ruler or a book or a straight edge to draw your line straighter than I drew my line, that would be best. Okay, so there it is. We're going to pick a point, test, and shade. Notice our 2x plus y is less than or equal to 6, so I'm going to assume we're going to shade below, but let's test 0, 0. So if we test 0, 0, 0 less than or equal to 6, yes it is. So here we're going to shade below. Okay. So there's our first constraint, the large pieces. Let's do the small pieces. 2x plus 2y is less than or equal to 8. We'll use the cover-up method to solve, so let's cover this guy up. We got 2y equals 8, divide by 2. All right, so we're first going to graph y equals 4. All right, let's cover up the other one. And we have 2x equals 8, divide by 2, so x equals 4. Okay, let's graph these two. X is 4, y is 4. It's going to be a solid line because of the equal sign. And we're going to pick a point, test, and shade. So again, I'm going to shade test 0, 0 because it's less than or equal to. So is 0 less than or equal to 8? That's true, so we shade below. And I'm going to shade the area that's already shaded. So I'm just going to like double shade this area. And it says right here, the feasible region is the area containing all the points that satisfy the constraints. So we talked about the feasible region. It's where it's double shaded, and what that means is any combination of tables and chairs inside the feasible region will work for our inequalities. So what that means is we could make, for example, one table and one chair, and it would work. We could make one, X is tables, one table and three chairs, so Y is chairs, and that would work. So any combination inside this red shaded area, that's going to work for our inequalities. All right, so graph the feasible region, done. Find the vertices of the feasible region. Oh, I should erase this right here. Oopsies. All right, so again, here's my feasible region. The vertices are the corners. So here are the vertices, the corners, and we talked about that before as well. So the vertices are 0, 0, 3, 0, 2, 2, and 0, 4. Okay, so that part is review, finding the feasible region, finding the vertices, but now here is the new part for linear programming. It's called the corner principle. The optimal solution will always lie on a corner of the feasible region. So what that means is one of these vertices is going to give us our maximum profit. Another one will give us our minimum profit. So the vertices will give us the maximum. It will also give us the minimum. The objective function is the profit function. Like, what are we plugging into to figure out maximum profit? And here, our profit function was what we plugged into here, which was $16 a table and $10 a chair. So I'm going to rewrite that. So I'll say P, profit, is $16 for every table, and $10 for every chair. So the objective function is, again, the equation that represents the goal of maximizing the profit or minimizing the cost. All right, so then here's our last step that we didn't do in the previous lesson, and that is one of these vertices is going to give us max profit. Let's figure out which one by plugging all of them in and figuring out which one gives us max profit. All right, so the first one I'm going to plug in is 0, 0. So the profit off 0, 0 just means we make 0 tables and we make 0 chairs, so the profit, of course, is $0. So that would be the minimum. All right, let's do the next coordinate, which is 3 tables, 0 chairs. 16 times 3 plus 10 times 0 is 48, I believe. Yes, 48. All right, so you can make $48 profit off 3 chairs. Let's do the next one. So that is 2 tables and 2 chairs. 16 times 2 plus 10 times 2, and that gave us $52. Oh, and this is what we had done before. And then our last one was 0, 4. So the profit off 0, 4 is 0 tables, 4 chairs at $40. So again, and we already saw this before, but now this is a faster way to figure out which coordinate will give us maximum profit. It's always going to be one of the corner ones of the feasible region. So when we plug it in, our maximum will give us $52 if we make 2 chairs and 2 tables. All right, so your assignment is to practice this. It's just one more linear programming problem. And I did put the answer key on Schoology if you have trouble setting up the equations, the inequalities, and solving.